So let's begin here the next main section of chapter 3. So we have looked at how to calculate the relative extrema, the relative min and max of a function using the first derivative to kind of determine the behavior of our original function, where the original function is either increasing or decreasing, and determining where we have a max or min, depending if we have a change in direction in our function. Now, the second section here of chapter 3, we're going to be looking at the second derivative and looking at what the second derivative tells us about our original function of x. Okay, and what we're going to do here is we're going to use the second derivative of a function in order to find what's known as the concavity of that function. In other words, the curvature, the type of curve that function seems to be displaying. Okay, now we have two types of concavity. A function is either said to be concave up or concave down. If our function is concave up, what that means is that our function has an upwards type of curve. It is opening upwards. In other words, it has a shape that looks like an upwards parabola. All right, so the curve of our function f of x is curving upwards. So like say, for example, it may look like this, like an upwards type of parabola. And when the function is upwards, when the function is concave up, that means our second derivative at any point along this type of curvature, our second derivative is going to give us positive values. Like if we pick any point along this curve, the second derivative will be positive, because what this is indicating is that our function, it's starting off as a decreasing function, but they're changing towards a increasing function. Okay, meaning the slope, it starts off negative, but it's heading towards positive values. Okay, so the curvature, the rate, the slope of our function is increasing. And again, the first derivative tells us about the behavior of the original function. Let's go back here. Okay, where the function is either increasing or decreasing based on the value of the slope. Okay, the second derivative tells us the behavior of the slope of our function, the rate of change of our function, which determines the curvature of the original function of x. Okay, so if our second derivative is positive, that means the slope of our function is heading towards positive infinity. It's heading towards increasing values. Our slope has started to increase. Okay, and in that case, when we have upwards type of curve, we say our function is concave up, upwards concavity. Okay, let me make that note here as well. Oops. All right, so our second derivative being positive means that the slope is increasing. It is heading towards positive infinity. Here we go. Okay. But if it's concave down, in that case, that would be the opposite. If our function is concave down, that means the curvature of our function is opening downwards. So the curve of our original function f of x is opening, it is curving downwards. So here we have an upside down parabola type of shape. Okay, draw that as well. And when we have an upwards, and when we have a downwards, upside down type of parabola type of shape, in that case, our second derivative, at any point along this type of curve, the second derivative is going to be negative. All right, second derivative will be negative. Meaning in this case, our function may have started off as an increasing pattern with a positive slope, but the positive slope is becoming more and more negative until eventually it starts heading towards negative values. All right, so when the second derivative is negative, all right, the second derivative is negative, that means the slope is decreasing. That is heading towards negative infinity values. Okay. So let's do a little graph here, a little example of a graph. Okay, we'll make this large enough. All right, so suppose our function has the following shape. So our function of x looks like this. No, it doesn't smooth out. Okay, so like that. Okay, so in the first part of this graph here, in the first half of this graph, our function has an upwards type of shape, meaning our function is concaving upwards. So here it is concave up. Where we have that upwards, the little cup, upwards cup. Okay, meaning our function in this case is being held up. I'll just do a color. I'll just, all right, if we draw right at this peak, what is it, right at this valley here, the valley is holding up this function. Okay, but at some point, it starts to change its curvature. Our function of x starts to change its curvature. I'll make a note here, f of x. And in the change of curvature, it starts to open downwards. So the cavity becomes down, it becomes concave down. So when we have the downwards curve, our function is concave down. And in this case, meaning that our function, after this peak, after it reaches that relative maximum at that peak, is starting to get pushed down. All right, so this case is being pushed down. Okay, and what we want to do here is we want to use the second derivative to determine the type of concavity and on which intervals our function will be concave up or concave down. But we also want to figure out at which point did the function change concavity? At which point did the function change its type of curvature? And that point, which may be roughly somewhere around here, that point is known as the inflection point. Okay, so the inflection point represents the point in which a function changes concavity, changes its type of curvature. And I'll denote the inflection point as IP from here on out. Okay, so let me make that note here. So the inflection point it is a point in which a function f of x changes concavity. Right, so the point where the concavity of a function of f of x, I'll just say f of x, changes. Either it goes from concave up to concave down, or concave down to concave up. Okay. So what we want to figure out here then is, how can we find these inflection points? Okay. So we want to use the second derivative, not only to determine the type of concavity our function has, but also to figure out where those inflection points are. And in order to do so, to find these inflection points, it is similar to finding the critical numbers from the first derivative. in order to calculate, in order to find these possible inflection points, we have to find the values, we have to find the zeros of the second derivative, meaning we have to find the values of x such that the second derivative will equal 0, or our second derivative will be undefined. So pretty similar to how we find the critical numbers of the first derivative. To find these possible inflection points, we got to find the zeros or the values of x, in which the second derivative will be 0 or undefined. Okay, so it won't be too much different of a process from what we saw from the previous section, except in this case, we're solving for the second derivative. All right. So let's do an example for this introduction video of 3.2. And for this example, let's also do a bit of review from the previous section. Let's find the relative extrema and concavity of the following function of x, where f of x is defined as x cubed plus 3x squared minus 9x plus 5. Okay, so we want to find the relative extrema and the concavity of this cubic function. Okay, so for part A, let's do the relative extrema first. Let's do a little review of 3.1. Okay, so recall, to find the relative extrema of a function, we had to find the critical numbers of that function. And to find the critical numbers, we had to calculate first, we have to determine the first derivative. So let's find f prime here, the first derivative of this function. All right, so derivative of x cubed, that's going to be 3x squared plus derivative of 3x squared, bring the power down, multiply the coefficients, decrease the power by 1 to give us 6x. And the derivative of negative 9x is just negative 9. Okay, so now set the second derivative equal to 0. All right, it's going to set f prime of x. Again, our first derivative was 3x squared plus 6x minus 9. Set this equal to 0. Try to see if we can factor out anything. Try to see if we can take out any common factor between our three terms here. What do 3, 6, and 9 have in common? A factor of 3. So we can factor out a 3 here, leaving us with the inside of x squared plus 2x minus 3 equal to 0. And now try to see if we can factor this out. Or if not, we have to use a quadratic equation, the quadratic formula. But in this case, I believe this should be factorable. So we're going to have 3 times x squared plus 2x minus 3. That gives us x plus 3 times x minus 1 equal to 0. And then solve for each factor of x. By setting each factor of x equal to 0, solving for x gives us x equals negative 3, positive 1. So here we have 2 critical numbers at x equals negative 3 and at x equals 1. And recall, after we find those two, and after we find our critical numbers, then we have to do the first derivative test. So we draw a number line. Probably make it bigger. So draw a number line and first draw our 2 critical points that we found, which one was at negative 3 and the other was at 1. So now pick any test points before, between, and after our critical values. So like say, in this case, negative 4, we'll do negative 3 and 1, we'll do 0 here, and then 2. And then recall, we plug in these test points into the first derivative. Now again, if we plug in our critical numbers back into the first derivative, since negative 3 and 1 came from solving this equation, when setting equal to 0, then that means if we plug in negative 3, it's going to give us 0. And if we plug in 1 into our first derivative, it will also give us 0. Okay, But now let's take these test points and plug into the first derivative. And let's see what we get. All right, so again, we're plugging -4 into the first derivative here. So 3 times -4 squared plus 6 times -4 minus 9, which should give us 15. All right, and then at 0, if we plug in 0 into the first derivative, it's just going to give us -9. And then at 2, we also get positive 15. Okay, so what is this telling us? Based on the first derivative, it seems that before this critical value at -3, since our slope was positive, that means our function was increasing. So our function was increasing, it was going upwards, and then it reaches that critical point at -3, where it zeroes out. And then after that critical point, since the test point here, after -3, since this test point is negative, that means our function was coming down. So our function is decreasing now. It is decreasing after -3, before once again, the function zeroes out at x equals 1. And then after 1, since our test point resulted in another positive slope, that means after the second critical point, our function started to increase once again, started to come back up. All right. So what do we see here now? Since our function was increasing, but then started to decrease after the first critical point, then recall that means then when the slope changes from positive to negative, then at that critical point, we have a relative maximum. So we have relative max at x equals -3. All right, but then after our function started to decrease, after our function started having negative slope, when it hit that second critical point, afterwards, it started to come back up. So the slope went from negative to positive, indicating then that at this second critical point, at the second critical number, we have a relative minimum at x equals 0. All right, so based on the first derivative and the first derivative test, it seems that we had a relative maximum at x equals -3, and to find the actual value of the maximum point, recall we have to plug in that critical point into the original function. So f at -3. Right, we're plugging -3 into the original cubic function of x cubed plus 3x squared minus 9x plus 5. And if we evaluate that correctly, we get a value here of 32. So our relative maximum is at -3, 32. Okay. And then we had a relative minimum at the second critical point, which was at x equals 1. Once again, to find the actual minimum value, we plug in 1 into the original function, which results in a value of just 0. So our relative minimum is at 1, 0. All right. So relative maximum at -3, 32, and then relative minimum at 1, 0. But that's only the first half of this problem, because not only do we want to find the relative extrema, we also want to determine the concavity of our function, where our function is concave up and concave down. All right. So again, this first part was just a review from the previous section. Now let's look at the new stuff here. Don't have too much room here, so I'm going to go to the second page. All right, so let's just rewrite our equation for part B. All right, so now for part B, we want to find the concavity of our function. So again, our function, f of x was x cubed. All right, it was x cubed plus 3x squared minus 9x plus 5. And for this function, we found the first derivative, f prime, to be 3x squared plus 6x minus 9. Okay, so to find the concavity, determine where our function could be concave up or down. To determine the concavity of our function, the next step here is to find the second derivative. All right, so it's going to be a three-step process, similar to what we did for part A. So first step, to determine the concavity of a function, the first step is to find the second derivative, f double prime of x. Okay, so in this case, the second derivative is going to be, let's see here, derivative of 3x squared, that's just 6x. Derivative of 6x, just 6. So 6x plus 6 is our second derivative. Okay, second step, we got to solve for the inflection points. And to solve for the possible inflection points, we have to set the second derivative equal to 0 and solve for x. So second step, set the second derivative now equal to 0 and solve for x. All right, so our second derivative, which again, we found to be 6x plus 6. We now want to set this equal to 0 and solve for x. So using algebra, subtract 6 from both sides, divide by 6 to give us x equals, I'll just do step by step. All right, so subtract 6 from both sides. We're going to have 6x equals negative 6. Then divide by 6 to give us x equals negative 1. So here we have the possible inflection point. And the reason why I'm saying possible is if there's no change in concavity, then it's not an inflection point. Right, so here we have our possible inflection point at x equals negative 1. Okay, so how can we determine now whether this inflection point here or whether x negative 1 here, if that is an inflection point or not? And how can we use that to help us determine the type of concavity of our function? Well, what we have to do now for the third step is pretty similar to what we did for critical numbers. All right, so to determine the concavity, we once again have to do that number line test. Now be careful, it's not called the second derivative test. The second derivative test is a different type of concept, which I'll talk about later on in this chapter. To determine the concavity, we do what's known as the general number line test, which is pretty similar to what we did with the first derivative test. So once again, we draw a number line, but in this case, on this number line, we draw the inflection points that we found from the second derivative. Meaning here we're going to plug in, we're going to draw first negative 1. All right, and just like we did before, pick a test from before, between, and after the possible inflection points that you found from the second derivative. So pick a test point before negative 1, I'll just do negative 2. Pick any test point after negative 1, I'll just do 0. And what we're going to do now is we're going to plug these into the second derivative, because we want to determine the type of curvature a function has before, between, and after these inflection points. Now, if we plug in negative 1 into the second derivative, if we plug in negative 1 to second derivative, well, since this was a 0 that we saw from the second derivative, then we plug in negative 1 back into the second derivative, it's going to give us 0. Okay, so let's take these test points and plug them into the second derivative. All right, so we're going to evaluate negative 2 in the second derivative. So we're going to have 6 times -2 plus 6. Again, we're plugging into the second derivative. So 6 times -2 plus 6, which is going to give us -12 plus 6, which gives us -6. So, all right. And now, oops, why did I say -2 twice? That should be 0. We're going to plug in 0 into the second derivative. So 6 times 0 plus 6. 6 times 0 plus 6 just gives us +6. Okay. So what do we see here? We see that before our second derivative became 0, before our x equals -1, the second derivative was negative. It was less than 0. And then after that inflection point at x equals -1, it became positive. So what is this telling me about my original function of x? This is telling me that before we hit x equals -1 here, before this inflection point, since the second derivative was negative, our function was opening downwards. It had a downwards type of shape before touching x equals -1. So our function was concave down before -1. Okay. And then after hitting this inflection point, the second derivative started to become positive. Meaning, when the second derivative is positive, that means the function is starting to open back upwards. So the second derivative is greater than 0, that means it is concave up. We have an upwards type of shape. So now this function is opening upwards after -1. Okay, so before -1, it is concave down. And then after -1, it starts to concave upwards. Okay, let me more formally write this here. All right, so based on what we found here, make sure in the room, our function, it is concave up. Now when we determine the concavity, we have to determine the interval in which is concave down and up. Again, the only 0 that we found from the second derivative, the only inflection point was at -1. Meaning before -1, if we test any value before -1, like -2, -5, -1,000,000, -5 billion, the second derivative will be negative. Meaning before -1, our function is opening downwards. It is concave down. So our function of x, it is concave down from, concave down. So I'll do down first. So our function is concave down here from -infinity, and got to use parentheses and we determine the interval here. Our concave down is our function of x is concave down from -infinity. From -infinity up to -1. Okay, and then it is concave up. It opens upwards after -1 to positive infinity. Meaning if you pick any number after -1, like 0, 5, 10, a trillion, the second derivative will be positive. Meaning it's opening upwards from -1 towards positive infinity. Okay. And since we have a change of concavity, since we went from negative to positive, since we have a change of concavity, then that means -1 is an inflection point. So we do have an inflection point, so -1, since there was a change in the sign of the second derivative around -1. And to find that inflection point, so we have inflection points, at x equals -1, and to find the coordinates of that inflection point, we plug in -1 into the original function. All right, so we're plugging -1 here into the original cubic function. And then if we evaluate that correctly, Then at -1, we should get +16. So our inflection point is located at -1, 16. All right. There we have this from the properties of this function based on the first and second derivative. With the first derivative, we found a high peak at -332. We find a relative low peak at 1, 0. And then with the second derivative, we have determined where the function has a downwards type of curve, where it is upwards, and where that change occurs, where the change in curvature occurs at -1, 16. Let's visualize this. Let's graph this here. All right, so we had x cubed plus 3x squared minus 9x plus 5. All right, let me set the window here. Or a quicker number is -3, -1, 1. I'll do -10 to 10. That should be fine. And for the y values, our minimum, what was our minimum inflection point? -2, 1. I'll do -5. And the max, I'll do 50 actually. And just give me more room for viewing. And then graph. So here we have our function. All right, so notice, here is our function's increasing until it reaches a relative maximum point here at -332, then starts to decrease until it reaches a low point here at 1, 0, and then starts to increase from there on out. And then look at the curvature of the function. Look at the curvature of this function. The function is opening downwards, it has a downwards type of shape, it has a downwards type of parabola shape. And then at some point, in this case at -1, which is kind of hard to get exact here. And then at -1, it starts to change, the curvature of the function starts to change and starts to open upwards. Okay, so before -1, our function has a downwards type of shape. And after -1, it starts to open upwards and concaves up. All right. So with the first derivative, we determine the high and lows of our function. And then with the second derivative, we determine the curvature, the type of curve of our function, where it's curving downwards and where it's curving upwards. All right. So let me pause this part here for 3.2 and do some more examples in the next video.